So now we want to look at how we can speed up this process of having that carry ripple through each of the 1-bit adders. Well, we'd rather it not, right? That's the slow path. So we want to actually figure out how to speed up that path. And so the next kind of adder that we're going to introduce, the carry lookahead adder, or the CLA, speeds up that path by basically calculating some of the carry outs ahead of time. And so we're going to compute the carry out for k-bit blocks, or for example 4-bit or 8-bit or whatever number of bit for blocks, and use what are called generate and propagate signals. Okay, so let's talk about what these generate and propagate signals are. So column I produces a carry out. So right, we have our different columns by either generating a carry out just of its own self, right? We have, for example, if we had 1, 1 in A sub I and B sub I, it would generate that carry no matter if a carry came in or not. So it either generates a carry or propagates a carry in to the carry out. So propagating means, well, now it depends on if there's a carry in. So, but if a carry in were there, it would propagate it to the carry out. So for example, if A sub I and B sub I were 0, 1, if a carry came into that column, yep, it would get propagated because at least one of those is 1. Okay, so we can calculate these generate and propagate signals for each column. Okay, so we have generate signal for column I, and we just kind of talked about this already. A sub I and B sub I both have to be 1 to generate a carry in a column, right? That will generate a carry. This 0, 1 for A sub I and B sub I. This case generates a carry. This one does not generate a carry. That one depends on now whether there's a carry in or not. Okay, so we can write that G sub I, this generate signal for column I, is equal to, well, both A sub I and B sub I being 1. So A sub I and B sub I. Now let's talk about propagate. A column will propagate a carry if A sub I is 1 or B sub I is 1, right? We can have this case, 0, 1. If carry comes in, yep, that gets propagated to the output. Here's the other case, A sub I, B sub I. Yep, if carry comes into that, it will get propagated to the output. And then we have, the kind of redundant case with generate, 1 plus 1, yeah, carry coming in is definitely going to generate a carry out on that, or, we actually have an overlap case there. So we can write this as P sub I is equal to A sub I or B sub I. So column I will propagate a carry coming into it if either A sub I is true or B sub I is true. And so we can write the carry out C sub I of a column in terms of these generate and propagate signals. So we have our original equation, right? We're going to get a carry out C sub I of that column if A and B are true. Okay, there's the generate signal. Or we wrote this before as A and C or B and C, just factoring out that C sub I minus 1. This is the carry in to that column. This is the carry out. And so we can see that A sub I and B sub I, this is when the column generates the carry within that column. Or it propagates a carry that came in, P sub I and the carry in, which is C sub I minus 1. And so we can rewrite that equation as G sub I or P sub I and the carry in, which is C sub I minus 1, the carry out of the prior column. Okay, so far with generate and propagate, well, it hasn't really been an advantage yet because this looks, this is a similar equation. We haven't sped that up at all there. So it really helps us have an advantage or decrease the delay when we calculate, propagate, and generate signals for k-bit blocks. Let's talk about that now. So before we do that, let's do a quick calculation of column propagate and generate signals. So remember, a column's going to propagate a carry that comes in if A or B is true, and a column is going to generate a carry independent of a carry coming in. It's going to generate a carry out if both A and B are true. Okay, so we can calculate propagate and generate signals. Propagate signals for this addition, right? We have A sub 0 or B sub 0. Yep, that's true. A sub 1 or B sub 1, 1 or 1. Yep. A sub 2 or B sub 2, 0 or 1. Yes. And the last one, A sub 3 or B sub 3. Yep, that one's also all ones. Okay, and then we can do the same thing for generate. Well, when are A and B both true? In this case, only in column 1. So A sub 1 and B sub 1 gives us a 1. Right, our generate signal, yep, that one would generate a carry out no matter if there's a carry in coming in or not. And then all of the other columns would not. So G sub I, all the other columns would not generate a carry in and of themselves. And we can do the same thing for, the addition on the right. P sub I, well, it's going to be 1 here, 0, because neither of the bits that we're adding together, A and B, are true, are 1. If we had a carry in coming to that column, that would just drop right into the sum bit. It would not get propagated to the carry out. And so we have a 0 for that column 2 in this case, and 1s for every other case for the propagate signal, the column propagate signal. For the generate signal, we have both A and B being 1 in column 3 and column 0. Columns 1 and 2 would not generate a carry in and of themselves. And so we can type that out and we get that same result that we just calculated. And we can see that, well, yes, if we can calculate now the carry using these column propagate and generate signals, we're going to get a carry out if, remember this is carry out, this is C sub I, if we either generate a carry within that column or we propagate a carry and we do have a carry in, C sub I minus 1. And we can see that as, as we add these together. If there's a carry in of 0, 1 plus 1, well, this one generated a carry, so that's how we got that carry out. G sub 0 was 1. P sub 0 was also 1, but the carry in that case was 0. So this carry out of column 0, C sub 0, that one right there, was because of the generate signal. Generate or propagate and carry in. Well, our carry in, this is C sub minus 1. So our carry in to an entire adder is called C sub minus 1. Okay, you can look at the other examples to see, okay, let's see, this one had a carry in. And so we had G sub 0, C out, column 0, C0, is G sub 0, well, that's 0. Or P sub 0, yep, that's 1. And C sub minus 1, yep, we had a carry in this case. We happened to, we just chose that carry in to be 1. And so that's how we got this carry out. That's what caused this carry out, C sub 0. Remember that is the carry out of column 0, carry in to column 1. This is column 1, this is column 0, 2, and 3. Okay, so there are column propagates and generates. And now we're going to start looking at our block propagates and generates. So we're going to use our column propagate and generate signals to compute these block propagate and block generate signals for k-bit blocks. So we're going to compute if that k-bit group would propagate a carry in to the carry out if it gets a carry in. So if it had a carry in, would it propagate it? to the carry out. We don't know if there's a carry in or not, but if it had a carry in, we want to compute whether that k-bit block, so for example, 4-bit block, would propagate that carry to the output of that 4-bit block. And we also want to compute if that k-bit block would, in and of itself, generate a carry out of the block. So will it generate a carry out just, on its own? Or will it propagate a carry if there's a carry in? We want to calculate those for these k-bit blocks. Okay, so let's take an example, 4-bit blocks. We're going to talk about a block propagate signal, and this nomenclature can be a little bit confusing at first. This is actually a single bit or a 1-bit signal. So P3 to 0 is a 1-bit signal. This is our block propagate signal. It's going to tell us whether that entire 4-bit block would propagate a carry in to its carry out. Okay, well, how do we calculate that? Well, let's see. Let's give some examples. So here's a 4-bit block, 0, 1. Let's just, yeah, so we'll do something like that. Okay, would that propagate a carry in? We don't know if there's a carry in, but if there were one, so let's say there were a carry in, here's our carry in to that block, would it generate a carry out? It definitely would, right? If we calculate our column propagates, P sub i's, P sub 0, P sub 1, 2, and 3, yep, that would propagate, that would propagate, that would propagate. All of those columns would propagate. So it's kind of like a relay game where, okay, this column propagated it, the next column, that column also propagated it to the next column. This column also propagated it to the next column. This column then propagated it to the output. Here's our carry out of that 4-bit block because it got propagated through all of the columns, each of those 4 columns. And so here's another example, a counter example where it wouldn't get propagated. So let's say, for example, we have this column right here, and let's just change it. We'll just change that bit, that B bit here, and say, okay, well, here's A 3 to 0, and here's B 3 to 0. And let's say we change that bit to a 0 here. We'll highlight it. Oh, well, so now that P sub I, that propagate for that column, in this case, column 2, right? Column 0, column 1, column 2, that P sub I is now a 0. So what happens? We still have a carry in that got propagated. So we're saying if a carry in comes in, what happens? Well, here's our carry in. It's still coming in. We still get that propagating it, that column 0. Column 1 also propagates it. What happens to column 2? 1 plus 0 plus 0, that falls right into the sum bit. And so now that column no longer gets propagated, and our carry out is 0. So in order to propagate a carry, we have to have that, through a 4-bit block, we have to have the individual column propagate signals be 1 for each of the columns. Propagate 0, and propagate 1, and propagate 2, and propagate 3. Right, if one of those drops the ball, like we saw here, right, this column kind of dropped the ball and said, hey, a carry coming into that is not going to get propagated. So that entire 4-bit block will not propagate a carry from its input to its output. It has to have all of the propagates be true. So now I've changed it so that it would propagate a carry in to its carry out. Okay, but regardless of what the bits are, we can calculate this. Remember, this is still a 1-bit signal, this block propagate signal. We want to know if that entire block would propagate a carry into the out to the output, to the carry out, by saying, well, P0 and P1 and P2 and P3, all of those propagate signals have to be true. Okay, so now let's talk about the generate signal. So here's some examples similar to the ones that I just went over. That one would propagate and this one would not, because as we see, this column right here happened to be a similar one. Drop the ball and that carry in does not get propagated to the output. Okay, so block generate signals. So now, independent of a carry-in coming into our block, we want to know, well, does this entire block generate a signal in and of itself, generate a carry-out in and of itself? So let's see some examples. Well, how could it generate a carry-out independent of of what the carry-in is to that block? Well, this most significant column, this is column number 3. Here's our column numbers. Column number 3, what if those were both 1? So we have A 3 to 0 and B 3 to 0. In this case, we have A sub 3 and B sub 3. They're both 1. Does that generate a carry out? Sure does, right? 1 plus 1, 2 to 0, carry the 1. Okay, so there's one case. So we could say this. Remember, this is a single bit signal again. G3 to 0 looks like a 4-bit signal, but it's a 1-bit signal. It says, hey, I want to know if this 4-bit block from 3 to 0 generates a carry. Well, one way for it to generate a carry is if, well, what happens in that column? Well, that's G sub 3 is going to be 1. Well, there's one way. So if the generate signal in the most significant column is 1, yep, that 4-bit block is going to generate a carry no matter what. Okay, well, that's good. Is that the only way? Let's think of some other options here. Well, what about, let's go to column 2. Let's see if column 2 generated a carry. So G2, if that generated a carry, would that be enough? Let's see, 1 plus 1 would be 0, and then it would generate a carry into the next column, to column 3. But what if column 3 were this? What if column 3 were like that? That's not going to make that entire block produce or, kind of generate a carry within itself. That would have to be, right, column 3 would have to propagate it. So now we're talking about our propagate signal, 0, 1, 1, 0, or 1, 1. Right, those are our options. So in this case, we'd have to have G2 being true and P3. It gets generated in column 2, and that carry that got generated in column 2 would have to propagate through column 3. There's another way we could do it. We could generate a carry within itself, generate in column 2, and then propagate through the next most significant column, like this, like we showed there. Okay, that's pretty good. Any other options here? Well, what about let's go to column 1, see what happens there. So we could generate a carry in column 1, right? We get A and B both being 1. A sub 1 and B sub 1, that would generate a carry. So yeah, we're sure that would generate a carry over to those next columns. But what would have to be true in order for this block to generate a carry within itself? Well, those would then have to propagate P2 through P2 and then through P3. Right, then we propagate that out to the output. Okay, so that's another case. So generate in column 1 and propagate through column 2 and column 3. Okay, so at this point, you can guess what the last case is. Well, what if we had a we generated in column 3, in column 0. So we have a 1 on A sub 0 and B sub 0. So we generate in that column. Well, in order for that carry to get all the way to the output, it has to propagate, right? We know we're going to generate a carry in that column. So C sub 0 is going to be true because guess what? It generated, right? It's going to generate that carry. G sub 0 in this case is 1. But we better make sure that propagates all the way through. So we get 1, 1 in that 0th column, but we better in columns 1, 2, and 3 get a propagate. G0 better propagate through column 1 and propagate through column 2 and through column 3 to get to the carry out of that block. So here's some examples where it is going to generate in column 0, and now it's going to propagate through the remaining columns. and make it to the carry out. So here's our carry out of this 4-bit block, or in this case, C sub 3. Right? And here's a case where it wouldn't, right? So that there's our last case. We had, well, generate sub of that 4-bit block. Remember, that's a 1-bit signal. So generate for the block, for this 4-bit block is, well, either generate it in column 3 or generate it in column 2, propagated through column 3, or generate in column 1, propagated through 2 and 3, or the last case, generate in column 0, propagated through 1, 2, and 3. Right. If one of those propagate signals, let's say propagate 2, for example, with 0, that 1 comes in, drops down here, and never gets propagated to the output. Okay, so we can write that in words. Carries generated. These are the way to generate a carry out within that 4-bit block by generating a carry in column 3 or in column 2, propagated through column 3, or column 1, propagated through 2 and 3, or column 0 and propagated through the remaining columns 1 through 3. And we write this, you know, like we just wrote it before. And then we can also, you know, write it in a different way, which you'll often see. We'll show it in circuit form by factoring out this P3 and get G2 or G1, P2, or G0, P1, P2. And then we can factor out this P2 right there. We're going to get G3 or P3 and G2 or G1, or let's factor that out. P2 and G1 or G0, P1. Okay, and that's usually easier for us to build, and we can build that with 2 input gates here. And so this is just the same equation with terms factored out. Right? These two equations are the same logically. This is the way to think about it, and then we can optimize it in that second equation. So now let's look at block generate signals. So a carry is, right, we're going to generate a carry out by either generating in column 3 or column 2 and propagating it through column 3 or blah, blah, blah. So let's see what happens. So this one, does this block of 4 bits generate a carry? Yep, it does, because G3, this leftmost column, is 1. We get a 1 here. And in fact, independent of what happens, if there's a carry in or what else happens to the prior columns, no matter what, 1 plus 1, 0, we're going to get that carry out of that 4-bit block. Right, we're going to get C sub 3, that carry out of column 3. Okay, because it was generated in column 3. Well, here's another case where we generate it in column 2. Here's column 2, and we propagate it through column 3. So 1 plus 1, 0, carry the 1, and it gets propagated, right? This propagate signal, P sub 3 equals 1, and G sub 2 equals 1. And so we get a 1 here, and it propagates it through column 3, and then we get that C sub, or that actually generate a carry from that block. Okay, and which will be C sub 3. And then here's another example. In this case, we have column 1 generating a carry. So we have column 1 has G sub 1 is equal to 1. Great. And it propagates through the next column. So 1 plus 1, 0. We don't actually, need to do that addition because we already are doing it in terms of propagate and generate, but just to show the analog. And for column 2, P sub 2 is equal to 1. Cool. Right, we see P sub 2 is equal to 1 because A or B, A sub 2 or B sub 2 is 1. And here we have P sub 2 is equal to 1. Cool. So it's going to propagate that carry that came in from column 1. But then what happens? So it propagated it, right? 1 plus 1, 0, carry the 1, propagates it here. What's wrong with column 3? Well, p sub 3 is 0. And so that carry that was generated in column 1 never makes it to the carry out. And so in this case, right, we have g sub 1, yep, that's 1, and 1 got propagated through column 2, but p sub 3, it did not propagate the carry. And so now we have, right, we get 0 here, or 0, or 0, or 0, and so this group of 4-bit blocks does not generate a carry within its 4-bit block. G3 column 0 is 0. Right, if we look at this does not generate a carry. And so, in summary, we have block, propagate, and generate signals too, where we want to know, hey, would the entire block propagate a carry that came into it? In this case, C sub I minus 1, would it propagate that to the output? Well, if all of the propagate signals are true, it would. Would it generate a carry out within, independent of the carry in to that block? Well, we derived that equation for G3 colon 0. Again, remember that's a 1-bit signal. And now we can write the carry out of that block in terms of these block propagate and generate signals. So C sub 3, carry out of that block, is going to be 1 if we generate a carry within that block, or we propagate a carry and there was a carry in. So let's take an example adder that's a 32-bit adder that has 4-bit blocks. So we have our block propagate signals made up of our column propagate signals added together, and our block generate signal. And then we can produce our carry out of that block using our block generate and block propagate signals and the carry into that block. So here's a schematic of our 32-bit carry lookahead adder, or CLA, with 4-bit blocks. And so we have our numbers, our inputs, blocked into 4-bit groups. So A3 to 0, B3 to 0, A7 to 4, B7 to 4, and so forth. Okay, so each of these 4-bit CLA blocks, right here, we're going to expand that and look at what's inside of each of those. So each of these blocks here. So each of these has, well, this looks familiar. There's our ripple carry adder with carry in, but you'll notice something strange about that ripple carry adder. What happened to its carry out? It's not there. The carry out of that block is actually being calculated by this circuit down here. So this circuit on the bottom is calculating our carry out of that 4-bit block. And so the sum bits are being calculated by our ripple carry adder on the top using the carry in. So the carry in is still rippling through there to produce the sum bits, but we're kind of fast pathing the carry out calculation here on the bottom. And so you'll see that, well, here are our column propagates and generates, and we're using that to calculate our block generate. Right, this is G sub 3 or P sub 3 and the rest of that, right? And here's our block propagate signal being generated by using our column propagates and generates. So we're not showing the gates here for these calculations, but we know that G sub 3 is A sub 3 and B sub 3. So that would be an AND gate. And this propagate signal is an OR gate, A sub 3 or B sub 3. Okay, so those gates aren't shown. Okay, so how does this work? It seems like this is a lot of gates down there too. So did we really make it faster? Well, let's look at the big picture here. So what happens at first? So all of these, so A sub 3, B sub 3, A sub 2, all of those A's and B's are available at time t equals 0. One gate delay later, either an AND gate or an OR gate later, we have all of these signals available. Right? All of our column propagates and generates are available. After one, either AND gate delay for generates or 2-input OR gate delay for propagates. And so those are available. One gate delay later, we get all of those signals. T gate, right? T AND or OR gate. Okay, what happens next? Well, after that one gate delay, then, well, this isn't the critical path, but this is, we go through 1, 2, 3, 4, 5, 6 2-input gate delays. So 6 2-input gate delays. Later, we're going to get all of our block generate signals. So not just G3 to 0, this is for all of them, right? G3 to 0, G7 to 4, G11 to 8, G blah, 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 right? All of these block generate signals, and turns out the propagate signal, that block propagate signal is just calculated faster. Okay, so we get, one gate delay to get to here, one 2-input gate delay. We get 6 2-input gate delays to get to all of them, not just for this block, for all of these blocks, propagate and generate signals. And now we can calculate the carry out of that block. So we can say, well, I have this signal, and I have my block generate signal and my block propagate signal. Now it's going to take just a 2-input gate delay to get through this and or delay of calculating this block carry out. So this carry out is going to be C sub 3. And then it's going to be C sub 7. And it's going to be the next one, C sub 11. And it's going to be the next one, C sub 15, C 18. Should actually be C19. C19, I'll erase that. C19, C23, and C27. And actually C31. So then we're going to calculate just through these 2 input gates, because time t equals 0, we start here, t equals 0, t equals 1 gate delay we get here, 1 plus 6 gates, so t equals 7 gate delays, we get to all of our block propagate and generate signals, and now those can speed through because we have all of those. These are happening in parallel. We get all of our block propagate and generate signals for all of these 4-bit blocks, and now it speeds through and calculates these block carryouts, C3, C7, C11, C15, and so on. And so let's look at this graphically, and that's all we need, right? Because so C in, this is that first C in, speeds through here, gives us C3. C3 goes out here, right from that block. It becomes a C into the next block. C3 produces C7. Great. C7 comes out, goes into the next block. All these signals are already generated, so they're just waiting for this C7, this block carry signal to come in. C7 goes out, produces C11. C11 comes in, right, the next block, quickly produces through this 2-gate delay, produces C15, and so on. Okay, so talk about these steps. Let's review them. Step 1, compute the column, propagate and generate signals. Compute the block, propagate and generate signals. In this case, for 4-bit blocks, but generally for k-bit blocks. And then the CN propagates through each k-bit propagate generate logic. And meanwhile, the ripple carry adders at the top are also producing the sum bits. And then the last step is actually we have to, right, even though we get that carry pretty quickly for that leftmost or most significant 4-bit block or k-bit block, we still have to compute the sum bits. That's what we're really interested in. We're just dealing with the carry because that's the slow path. So we still have to actually ripple through that last k-bit block to compute the sums. And so we're going to compute our G's and P's, our generates and propagates for columns using AND and OR gates, G sub i's, P sub i's, and then we're going to compute for each of the k-bit blocks. This happens in parallel, right? This happens in parallel. This happens in parallel. That's where we're gaining here, is we compute the column and block generate and propagate signals in parallel. And then we're going to speed through these last 2 gates to quickly calculate these block carry out signals. C sub 3, C sub 7, C sub 11, C 15. And then this last one, right, we finally get our last carry in here for that last block, or C27, comes in here, and well, now we still need to ripple through these last 4 sum adders, full adders, to get our actual sum bits, right? Sum for the last 4 bits. And so here's that picture again. It's going to take, well, let's figure out the delay. So it's going to take 1 gate delay here. So T gate, 1 gate delay, plus 6 gate delays to get to our, for all of them, remember, not just for this block, but for all of these. We're calculating these in parallel, so it takes 1 plus 6, 7. And then it's going to speed through 2 gate delays. So we got, 2 plus blah, blah, blah for each of those. And finally, it gets to this last block, and we have to do the full adder delay for that. So K times T full adder for that last block. And so we can calculate the delay. It's a little more complex, but we have, well, the delay to generate the individual column propagate and generate signals. So TPG is what we're calling this. We know that's just 1 gate delay, 1 2-input gate, either an AND gate or an OR gate. The delay to generate the block propagates and generates, that's this next amount. And we know that that's 6 2-input gate delays. In this case, because we have a 4-bit block, but maybe it'll be different for different k-bit blocks, but in our case, 6 2-input blocks, or input gates. And then n over k minus 1, we had 32 and 4. So 32 divided by 4 is 8. Minus 1, we had 7 and OR gates. And so it's going to go through those, right, those first 7. And then when it gets to the 8th block, right, it's going to go through those AND OR gates. When it gets to the 8th block, we get our C, in this case, C27 coming in. So it's going to go through 7 of those, 1, 2, 3, 4, 5. I'll go ahead and draw them. 6, 7. And finally, when it gets to that last block, the critical path is going to be through our full adders. So we're going to have K full adders as we ripple through those last 4 adders and generate the sum. And so our equation is the delay of a carry lookahead adder, the critical path, is TPG plus TPG block plus n over k minus 1. In our example, it was 7. Through the and or gates, calculate those, make the final calculation for the block carryouts, and then the rippling through the last group of k-bit blocks to produce the sum bits, or k times t full adder. So an n-bit carry lookahead adder is generally much faster than a ripple carry adder for n greater than 16.